Hello, everybody. Hello, hello, hello. Hopefully everyone can see me and hear me. Welcome to another A-Level Chemistry Sunday session. Please feel free to say hello in the chat. Hello, my name's Alyssa. I'm one of the tutors. So welcome to our A-Level Chemistry Sunday session. Please feel free to say hello in the chat, but also download today's slides. They should be in the description underneath our YouTube video, so you can download the slides. That means you can keep them for revision. It means that you can use them for this session now to annotate. It means that you can use them in a couple of days' time to remind yourself of what we went through, because spaced learning is always very good. So yeah, please feel free to download those. But hello, please do feel free to say hello in the chat. Hello to Abin and Turbo as well. I don't know if Turbo is your real name, but hello anyway to you guys. Yeah, please feel free to say hello in the chat. Welcome to our A-Level Chemistry Sunday session. This is on dynamic equilibrium, so what equilibrium is, etc. So we'll just give it another 30 seconds or so in the hope that my laptop still copes, and then we will get started. Hello Isabel, welcome, and hello Neha. Please let me know if I pronounced your name wrong, Neha. And hello Mel as well. Welcome everybody. How's everyone doing? Is everyone feeling all right? Everyone enjoying their Easter break, if they've had an Easter break? I know that, yeah, we've had such a mixture of weather here. I don't know if you guys are the same, but we've had a very odd set of weather. In fact, it's only just started snowing, even though it's also gorgeous sunshine. Very odd. Hello Ada as well. I don't know what your name would be. All MQ solution. But hi guys, right, so I think we will start ourselves going, and then if anybody joins later, then they can just join anyway. But hello to everybody. Hopefully everybody is doing well. We will get started then on this Sunday session. So today we're looking at A-Level Chemistry, and we're going to focus specifically on dynamic equilibrium and what this is. So a little bit about me. If those of you haven't seen any of these sessions before, I am one of the tutors here. So, oh, hi Jennifer as well. I'm one of the tutors here on SnapRevise. I am the lead GCSE chemistry teacher, but I also teach A-Level chemistry for SnapRevise, and I've been teaching A-Level chemistry and GCSE science. Hi Amy, welcome, for 6 years now. Well, actually over 6 years, but it's something that I really enjoy, and yeah, really nice to have the opportunity to offer these sessions to you guys on YouTube. Hello, Mustafa. Oh, I might have not pronounced that right. Sorry, my chat's very small. Hello, Raven. Hello, Adam, as well. Hello, Blue Defender. Oh, sorry, it's Mushafi. Sorry, I definitely pronounced that wrong. But hi, guys. Welcome. I'm Alyssa. I'm one of these teachers, one of the SnapRevise teachers. Just letting you guys know, if you're interested, there is a code for a 1 week free trial for our tutoring service. So if you're interested in having access to these kind of web sessions on a regular basis, then please feel free to make a note of this code. There will be a, I'll put this on the final slide as well, so you can use it then. It will write it down then if you'd like, but it gets you a 1 week free trial to the tutoring session, so you can see what it's like doing it on the website, although they are very similar to these sessions. But please use the code tutor7, and the discount code is in the chat for you as well. Hello, welcome to those people that have just arrived. Hi, nice to see you, and welcome to our A-Level Chemistry. So over the next probably just less than an hour, we are going to be looking at understanding the concept of reversible reactions and equilibrium. So what are they? What do they mean? How do we define them in an exam? We're going to have a look at Le Chatelier's principle. So what this means, you might have heard of it as the equilibrium law as well, but I'm gonna refer to it as Le Chatelier's principle, and we're going to apply Le Chatelier's principle to different environmental changes as well. So see what happens when we make changes. What does Le Chatelier's principle mean for our equilibrium? Things we're not going to look at, though, is the equilibrium constant or calculations using the equilibrium constant. That is a separate web class. But please feel free to ask as many questions as you want. The more you guys interact, the more you're going to get out of this session. So please feel free to ask questions on the chat. If I can answer them, I will. If I don't answer your question, it's normally because it's disappeared on my chat and I haven't seen it. So please feel free to ask it again. And please feel free to answer each other's questions as well, because you guys are amazing and understand things brilliantly. So if you can explain something, then please feel free to. Not only is that good for you because you learn by explaining, but it's good for everybody else to hear different points of view. You know, as a teacher, I have a specific way of thinking sometimes, so in terms of what I want to convey, and it might be useful for you guys to explain things to each other as well. So please feel free to interact. But hello to everybody. Hello to somebody great as well. Nice to have everybody here. So if you haven't been to one of these sessions before, just to let you know, we put the specification points for 3 main exam boards in our PowerPoints, which you can download in the chat in the description. And this is a way for you to check what it is that your exam board needs from you, or wants from you, or is expecting from you. So these are the spec points from AQA. These are the spec points from OCR. And these are the spec points from Edexcel. Notice here that in Edexcel, we don't state Le Chatelier's principle. They don't talk about Le Chatelier's principle, but it is here. That's what this section means. It's talking about Le Chatelier's principle and the effects of change on equilibrium. It's just that we don't call it, Edexcel doesn't call it that, but it's still completely relevant to you guys. Okie dokie, so let's fold this down. What do we already know? So I would love you guys to pop as much in the chat as you can. Like I say, the more you give, the more you put into this session, the more you're going to get out of it. So can you come up with a definition, or can you come up with a description of a closed system? What is a closed system? And hello to KK and hello to Jessie as well. Nice to see some familiar faces, familiar names even. Welcome back to those of you who are regulars, and hello to those people that this is the first time. Very nice to have everybody here. So yeah, pop in the chat then a description or an idea of what you think a closed system is. And then when I talk about a system and the surroundings, what am I talking about? What am I describing there? If you can come up with a good definition, this would be great. But otherwise, describe to me what you think we're talking about when we talk about a closed system or a system and the surroundings. What is it? Ah, fabulous, guys. So Fatima looks great. Ella, that looks great as well. Myas, that looks fabulous. And Ancella, that looks lovely as well. Good. Now, I think some of us are going to have to be a little bit more specific. However, I'm really liking these definitions. Very nice. Lovely. Fantastic. So the closed system specifically is talking about the fact that no energy or matter can leave or enter the system, which is what lots of you have said, and nothing is transferred to the surroundings. So let's pop something in like that. A closed system is a system where no energy or matter can leave or enter. What am I doing? Enter the system. Please feel free to let me know if you can't read any of my handwriting, or if you want me to explain something in more detail, or if you just want me to write something again, or if I make a mistake, because I sometimes do. Please let me know in the chat if there's anything that I can help you with, or if you can't read my handwriting or something. So a closed system is a system where no energy or matter can leave or enter the system. Actually, I don't need to put the system on the end, do I? That doesn't make sense. where a thing can leave or enter, nothing is transferred to the surroundings. Now I've used these two words, system and surroundings. What do they mean? What am I talking about when I talk about the system, and what am I talking about when I'm talking about the surroundings? Good, nice, Sarah. Very nice. Is the Earth in a, is that a question, Candy? Is the Earth in a closed system? Is that a question? Because technically, I'm not sure I would say the Earth is in a closed system, because matter and energy can leave. So I'd say perhaps not. We might want to consider it as a closed system in order to be able to discuss kind of weather patterns and that sort of thing, because it might make it easier to make models with it. However, I'm not actually sure it is. Good, lovely. So let's put those in. So the system is the matter or reaction that you are studying. So when I'm talking about a system, often I'm talking, oops, I can't spell. Often I'm talking about a reaction. And then that means I'm considering the reaction as a whole. So the system is the reaction. And then the surroundings is just any other matter outside of the system. Any other matter outside the system. Of the system. Lovely. And what about these terms endothermic and exothermic? What are the definitions of endothermic and exothermic, guys? Zara straight in there. Very good. What are these definitions, endothermic and exothermic? Which one's which, and how do we work it out? Oh, nice, Maya. So that's a good one. I like that. Exactly. Good, Fatima. Which one's which, though? Can we work out which one's which? Lovely. Very nice. Okay, so there's some really good definitions going on here. I think I will say when we're talking about endothermic, we're usually talking about an endothermic reaction. So I'm going to pop in reaction. It looks like lots of you have got it nailed anyway, but that's usually we talk about that being a heat transfer or energy transfer, but it's in the form of heat transfer. That's an F to, oops, no, or to the system, sorry. From the surroundings to the system, I'll put, because then I'm being complete, although I might run out of space, to the system. Oops, I did slightly. And therefore exothermic is the opposite. Exothermic reaction is a heat transfer from the system to the surroundings. So again, when I'm talking about the system, I'm talking about the kind of the reaction, but everything that's going on in the reaction. So reactants and products. Lovely. Yes, Ella, the videos are on the channel, as well as all our past videos as well. So please feel free to go back and watch previous videos. You can rewatch this one as well. And yes, please feel free to do that. They should all be on there pretty much straight after our session. So feel free to go and look at that. And just to double check, because I haven't mentioned it yet, a nice way of remembering, if you can't remember which one's which, is using the beginning of the words, the ones that I've underlined. We can say energy enters the system and energy exits the system is a nice way of remembering which way is which. So endothermic energy enters and exothermic energy exits. You just have to remember it exits the system. Lovely, good. Okay, so let's look at dynamic equilibrium then. What is it and what are we talking about? So reversible reactions. A dynamic equilibrium has to occur when there is a reversible reaction. So first things first, something we look at key stage 3 often is an irreversible reaction, or we just tend to call it a reaction because we haven't looked at reversible reactions. But what is this? What is an irreversible reaction? How might we describe an irreversible reaction? And therefore, what's a reversible reaction? How can we describe a reversible reaction? What do we think the phrases are that we need to use? Or are there any keywords we might want to include? So what is irreversible reaction, just a normal reaction. What are we talking about when we talk about a normal, straightforward, irreversible reaction? And what is therefore a reversible reaction? Anybody know? So for example, I'll give us an example. Just A plus B goes to make C plus D is an irreversible reaction. Good, lovely. So an irreversible reaction only includes a forward reaction. It can't be undone. You can't form the reactants again. Lovely, this is all great. It doesn't allow a backwards reaction. The reactants make a product, but the products go back to make the reactants. Brilliant, good. It looks like we've got a good understanding of that. So this is an irreversible reaction, is a reaction with only a forwards direction. Reactants make products. Lovely, well done. It can't be undone. Yeah, you can't reform the reactants again. Brilliant. But therefore, you guys are exactly right. A reversible reaction is one which has both a forward and a backward reaction. Reverse reaction is a reaction with both a forward and backward direction. Oops, I'm writing too fast. Direction. Lovely. So we can reform the reactants again. And then we have to do it with this funny little double-headed arrow, or not double-headed, what's it called? It's a double directional arrow with half an arrow on the top, half an arrow on the bottom, and then both pointing in different directions. Hello, welcome, welcome. No worries about being late. That's absolutely fine. Welcome. Kashika, welcome, welcome. I'm Alyssa. I'm one of the tutors. We were just talking about reversible reactions, and I was just going to give us an example of one. Could be, for example, the formation of esters. So if we have a carboxylic acid, whoops, and an alcohol, a reversible reaction can occur to form an ester and water. And that means the forward reaction we would then call, because it's releasing water, we call it condensation. And the backwards reaction, because it is using water to break a bond, we can call that hydrolysis. There we go. Nice, Rachel. Very good. Yeah, lovely. No, Farsan, sorry. I said at the beginning of the thing, which you might not have been here for, but we're not going to be covering KC today. We're just going to look at the theory of equilibrium and Le Chatelier's principle. Okie dokie. Okay, so you need to be well acquainted with these kind of graphs. You may be required to draw one in an exam, although you might not. So, for example, if we are taking the formation of N2O4 from NO2, in this case, which colour, if I were to draw this, oops, go forwards. If I were to assign the colours of the line on here, the red and the blue, which one's which? Given the way that I've written the equation, which line shows the concentration of NO2 and which shows the concentration of N2O4? This is an hour long. We'll finish at 5, just before 5. This is some Le Chatelier's principle is often AS actually, it's covered in year 12, I should say, but you can be assessed in both exams, obviously. Lovely, guys, well done. It looks like everybody has got it pretty much correct. So we've got our NO2 is the formation of the oh no, No, other way around. I've got it wrong on my notes, that's why. It must got to be that way around. The red line is N2O4 and the blue line is NO2 because we're starting with an amount of our reactant. So we must have a starting concentration and we're starting with 0 product, but we have to form some product. Apologies, doesn't help if I've got it wrong in my notes, does it? Good. So Liz, in this case, if we look at the red line, we're starting at 0. The concentration of whatever the red line is showing starts at 0. So it must be a product because we must start with none of it. So that must be our product. Whereas our blue concentration, we start with an amount of whatever is the blue one, and then it decreases. So in that case, it must be a reactant because we started with lots of it. And then as it gets used up, it decreases. Okie dokie, well done, guys. And on this graph, how, oh, bless you. Well, thank you for coming anyway. I'll see you soon. Thank you, Kishika. So on this graph, how do I recognize at which point the equilibrium has been met? How do I know where equilibrium is on this, dynamic equilibrium is on this graph? Thank you, see you later. How do I know where it is? Well, we've got 2 options at the moment. It's either where they cross, where that point there, or it's this point here on the green line. Good. So, okay, we've still got 2 options. If we think in a closed system at dynamic equilibrium, one of the defining characteristics is the rate, the concentration of the reactants and products remains constant. Not the same. Notice how I have not said the same. They have remained constant, or they don't change. Okay, and that is how I know that it is an equilibrium. So that is at this point. Equilibrium is reached when they remain constant, because at this point and this point, where our green line is, at this point in time, our concentrations of our product and reactant remain constant. From then onwards, they don't change. So that is where equilibrium is reached. All this bit is telling me here, where they cross, is when they both have the same concentration. So that's not actually when equilibrium is reached. It's just when they have the same concentration. Could be at any point. Okie dokie. Yeah, so green dotted line. So do we assume the concentration is amount of substance? Basically, yes, Odie, that's a good question. But yes, because you're not changing the volume. You're not going to be adding in any solvents. So you can use concentration exactly as a measure of amount. Yep, very good. And so if our concentration of reactants and products are remaining constant, what do we know about the rate of the forward and backwards reaction in dynamic equilibrium? If the rate of if the concentration of the reactants and products remains constant, what do we know about the rate of the forward and backwards reaction? The rate of the forward and backwards reaction they are equal. Good, very good. Are equal. That means we are making reactants at the same rate that we are making products. Fabulous, well done. And in this case, you could say the same. You can use the term the same, but I like the fact that we're all using the word equal. I think that's a great word to use because then we forget about the word the same and we're a bit more specific about it. So yeah, very good, guys. Well done. Note that this is in a closed system. It has to happen in a closed system. Otherwise, we'd end up losing reactants or products and the rates would never get to equilibrium. They'd never get to the point where they are the same. So it has to be in a closed system. If you have any questions at any point, please pop them in the chat. I do try and check it regularly. But if I ignore you for any reason, please pop it in again and I will try and answer it. So let's have a look at Le Chatelier's principle. Le Chatelier's principle tells us how the equilibrium concentrations will react to changes in the environment, i.e. when we put a stress on a system, how does our equilibrium respond? So hopefully you guys know this law already. When a system at equilibrium is subjected to external change, as in we make a change to the system. So we try to change the pressure, we try to change the concentration, we try to change the temperature, etc. So when a system that is at equilibrium is subjected to external change, when we try to change it, the system reacts or adjusts to reverse that change. Or we could also say to minimize the effects of the change. Oops. No, there we go. Minimize the effects of the change. So it works to try to stop the change from having an effect on the equilibrium. Good, it shifts to resist the change. I like that phrase, yep. The position of equilibrium moves to oppose the change in conditions. Very nice, yeah, really nice. So for example, and we'll go through this in a little bit more detail in a minute, but if we have reactants going to products and our equilibrium, and I've added in some reactants, which way is my equilibrium going to shift? This is supposed to be reversible, by the way. Is this an OCR definition for the exam? So in terms of the exam boards, actually all 3 exam boards, as long as you are talking about it being a system at equilibrium, you definitely need to say it's at equilibrium. You need to say something about there being an external change, but you could call that a stress, or you can call it a change. That's fine. So you have to say something like that, and you have to say something about it, the system adjusting or the equilibrium adjusting to reverse the change or to minimize the change. As long as you say those 3 things, you will get all your marks in the exam. If you want to memorize an exact definition, then please feel free to have a look at your textbook. It might provide you with one that you can learn rote by rote, or learn one like this, because this should get you all the marks. Could somebody, if you can remember, pop in the chat what the definition is for a closed system, so that Kurt can have a look at that, because we did that earlier. Hopefully somebody's got that to hand. Can you use it in CIE? Yes, I'm sure you can use it in CIE. Okay, so equilibrium. If I was saying, if we've increased the amount of reactants, then what's going to happen to the equilibrium? Thank you, Ad. That's brilliant. Thank you very much. They might, Jessie, they might call it Le Chatelier's principle, but what they'll do is they'll say the equilibrium law is known as Le Chatelier's principle, and then they'll say explain how, whatever, or explain what will happen when, etc. So because it's not specifically mentioned in the spec, they should have to provide you with information to tell you what it is before they then expect you to use it, if that makes sense. They might not at all. They might literally just ask you a question like, what happens to the equilibrium when, blah, blah, blah. So they might not even mention an equilibrium law or Le Chatelier's principle at all. But if they do, then hopefully they should provide you with some sort of tip or some sort of information to help you get to that, to understand what it is, basically. Good. Thank you very much for giving those system definitions. That's great. So if we've increased our reactants, our equilibrium is going to shift to the right. And we'll go through this in more definition, in more detail in a minute. If we've got an increase in product, then our equilibrium shifts to the left. But yes, we're going to go through this in more detail in a second. Good. Would it shift to the left or the right on the graph? We wouldn't see any change on that graph because at the moment, on our graph, all it's showing is the rates of the forward and backwards reactions once they're at equilibrium. So our graph would actually change probably fairly dramatic, well, not that dramatically actually, but the graph would change if you then subjected the system to a change. So you wouldn't be asked to draw the graph. You'd only be asked to describe what would happen. So I wouldn't worry about the graph, but you can think about that when we talk about it in a second. Think about what you would see, what you would say. Okay, so well done, guys. How are we feeling at the moment before we have a go at a question? How is everybody feeling? Yes, but KK, we will look at that in more detail in a second in the next section. So how is everybody feeling? Give me a 1 in the chat or a smiley face if you're feeling good, if you're feeling confident about what we've just talked about. 2, if it's all right, you probably need to do a little bit of your own revision, or maybe you need to memorize some things or do some practice. And then 3, oh gosh, no, I'm feeling a little bit rubbish, totally confused. This has gone way over my head. How is everyone doing? Fair enough, lovely. So a mixture, that's absolutely fine. Great, fabulous. So don't forget, please feel free to ask questions in the chat if you have any issues that you want me to try and explain or come up with another way of thinking about, then please do that, because I will try my best and other people can help you as well. And if you haven't, if you've only arrived fairly recently, please feel free to download these slides, because there's a link in the description under the video for you to download these slides so you can use them again, you can use them now, you can save them for revision, etc. So please feel free to do that as well. Okay, let's have a go at an exam question then. This is a nice, fairly simple exam question, or fairly common exam question, maybe I should say. So ammonia is manufactured by the Haber process, in which the following equilibrium is established. Give 2 features of a reaction at equilibrium. 2 marks, 1 for each of them. What are they expecting from us here? What are they expecting us to say? Give 2 features of a reaction at equilibrium. How do we know? What are we looking for when a reaction is at equilibrium? What can we say? Good examples of closed systems. I quite liked, so Raven, this is in answer to your question, what are some good examples of closed systems? While I'm waiting for people to answer these questions, I quite like using a Coke bottle, because when it is closed and sealed, it's not completely a closed system because there's still going to be energy transfer. So you'd have to put in a lot of effort to stop there being energy transfer, but it's a good physical transfer closed system in which there is an equilibrium. But when you open it, you release that closed system, and therefore it can it is no longer a closed system, and you lose the equilibrium. Hence, your Coke goes flat. So I quite like that as trying to think about equilibrium and closed systems. That's quite a good one. Otherwise, you have to work very hard to make it a closed system, because you have to stop transfer of energy and transfer of matter. So it's got to be completely closed, you know, lots of, what's the word? What's it called when you protect something from heat loss? Oh, brain. What's it called? Not packaging. When you're when you use polystyrene to keep something, insulation. Thank you. My brain was not happening with that. Could not get that. Thank you. Insulation. That's exactly what I was looking for. Lovely. Good. Somebody asked a question just then, which I haven't seen. How do you know if it's a closed system? You just have to try and work out if it should tell you in an exam if what you're considering is a closed system, but otherwise, you know, read through the information given to you and work out whether or not you can see any transfer of matter or energy. And if you can't, then it's a closed system. Oh, I've got no idea, Liz, I'm afraid. I'm not sure. I'm not in charge of that. I assume they will be done fairly quickly, but I don't know any further than that. It's a bit rubbish, sorry. Okay, so I think we have said we need to quote these two phrases that we had before. The concentration of products and reactants remain constant. And again, we do not say the same because they're not the same as each other. They're not necessarily the same as each other. They might be, but they almost definitely are not the same as each other, but they just remain constant. They stay the same over a period of time. And good, but also the rate of the forward reaction is equal to the rate of the backward reaction. Oops. The rate of the backwards reaction. Or the rate of the forward and backward reaction are equal, something like that. Is good. 1 mark for each of those points gives us the full 2 marks. So in this case, so Mercy, when this reaches equilibrium, when this system reaches equilibrium, then the rate of the forward reaction, the rate of nitrogen and hydrogen turning themselves into ammonia, and the rate of ammonia turning itself back into nitrogen and hydrogen again is equal. So there won't be a change in pressure because the I know what you're thinking about. I know what you're considering, but the rate of them changing will happen so that there isn't a change in pressure, or every time there is a change in pressure, the system would adjust itself ever so slightly to allow for there not to be a change in pressure. So we'll look at that in a second when we do the application. But it's a good question, very good question. But we would consider there to not be a change in pressure. Okay, so Victoria, sorry if I've pronounced your name wrong. Glittering Star has answered your question there. This is just describing what we're looking for when we've got a reaction at equilibrium. So what are we looking for? We're looking for concentration of products and reactants to remain constant and the rate of the forward and backward reaction to be equal. Okay, lovely. Right. So next part 2, which I need to whiz on a little bit because I've been talking a bit too much. The effects of concentration. So for any reactants and products in solution, the position of the equilibrium will be affected by changes in concentration. So this is obviously, when we're talking about concentration, it has to be in solution. So if we are increasing the concentration of, so that's what those square brackets mean. Hopefully you guys are okay with that. If we're changing the concentration of A, i.e. we are increasing A, and I'll stay in green because I'll use a different color in a second. So if we increase A, you can kind of think about it a bit like a seesaw if you want. But if we're increasing A, then the system wants to remove that A. So if it wants to remove the A that we've just added, it's going to shift the equilibrium in the forwards direction. So we're going to push the equilibrium to the right. So we're going to have more forwards reaction to use up all of that A, which means the forwards reaction is going to increase. But because the forwards reaction has increased, we're then going to get more C and D produced. So an increase in A, if we increase the concentration of A, it shifts the equilibrium, equilibrium to the right to use up the extra A, and this produces more, producing more C and D, more products. Actually, I'll put products. Products, C and D. And if I change color, so we can do the other one. So at the moment, I haven't given you any information about the energy yet. word. We haven't spoken about that yet. We'll come on to that later. At the moment, there isn't any information about the energy of the forward or backward reaction or of reactants or products. So, this is, so extra A is because if I've increased the concentration of A, that means I must have added more of A in order to increase the concentration. Having said that, technically I could have removed solvent, but I'll put A in a concentration brackets because that might make, I should be in green. I'll put A in a concentration bracket just. So that's what I'm talking about. It's because if we're increasing the concentration of A, then we've got extra A per decimeter cubed. And so in order to use it up, to go back to our equilibrium again, we're going to need to use up the extra A. So in doing that, we produce more products. Okay. And therefore, so yes, increasing concentration of A in this case is going to have an impact on the product formation, definitely. Yep. And then if we do the same, but in reverse, an increase in C. So if we increase the concentration of C, product, then it's going to shift the equilibrium in what direction? If we increase C, what's going to happen? Good question. Is the amount of products the same as yield? No, because usually when you're given a yield, you're looking, I think, as somebody has said, at a specific product, at your desired product. So not necessarily, I think is the good. Yes, well done, guys. It's going to shift it to the left in the direction of the backwards reaction. So this shifts the equilibrium in, to the left. Or you can, it's perfectly acceptable for you to say in the backwards direction. Again, we're using up the, and I put it in quotation marks, extra concentration of C. However, we've done that. Therefore, in this case, we're going to produce more reactants. A and B. Okie dokie. What's meant by yield? Yield is, we talk about yield as an amount of something that's been produced, usually. Okay, let's move on from concentration then to, because I think concentration is probably the easiest one to think about. Let's have a look at the effect of temperature. So in an equilibrium reaction, if the forward reaction is exothermic, i.e. the enthalpy change is negative, it is releasing energy to the environment, the system is releasing energy, so the enthalpy change is negative because the system has lost energy. So if the forward reaction is exothermic, and the backwards reaction must be endothermic because they're opposites. So if you need to put in energy to go one way, then you have to, it's going to release energy to go the other way. So they are opposites to each other. And vice versa. So for example, if we have our forwards reaction is exothermic, as in delta H is negative, so it's exothermic, then if we increase the temperature, what's going to happen to the equilibrium? Anybody know? Oh, lovely. Thank you for that, Alyssa. That's great. Thank you, guys. That's brilliant. Fabulous. Okay, good. So if we increase the temperature, and you can consider it if you want in terms of producing heat. So if this is exothermic, then it's also giving off heat. And then you can consider it just like we did with the concentration. So if we're increasing the heat, we're increasing the temperature, so we're increasing the heat, then it's going to shift the equilibrium back in the endothermic direction. So it shifts the equilibrium in the endothermic direction, or in this case, left. so that we have more of the backwards reaction happening to, again, use up the extra heat energy, i.e. we're going to want lots of endothermic reaction happening because the endothermic is taking in heat. It's going to use up that extra heat that we've put into the system by cranking up the thermometer, cranking up the temperature. And conversely, if our reaction, our delta H is positive, i.e. is endothermic, if our forward reaction is endothermic, and if we increase the temperature in an endothermic reaction, then again, this means our backwards reaction is exothermic. So if we're increasing the temperature on an endothermic reaction, then the opposite is going to happen again. It's going to shift the equilibrium to, oops, in the, in this case, endothermic direction again. But in this case, that's to the right. I just realized I didn't spell direction right in the previous one, never mind. To, again, quotes, use up the extra heat energy. So when you're looking at temperature, as long as you know which direction is exothermic and which is endothermic, you should hopefully always be able to work out which way it's going to go. It's going to go to use up the extra heat or to produce extra heat if it's the opposite. So hopefully we can work out those. I was just going to spell that correctly. Anybody not happy? So the forward reaction is endothermic. Yes. So in this case, if we increase the temperature, it's going to increase the endothermic direction because it's going to want to use up all of the energy that we've just put in. So it's going to go to the right in the endothermic direction on the second one. Yeah. Oh, have I written it the wrong way around? Oh, I have, sorry. That should be the other way around. Delta H is greater than 1. Apologies, because this is talking about an exothermic reaction and it's talking about the forwards reaction being exothermic. So that's, sorry, our delta H values were wrong there. Good spot, well done. Delta means change in. So is there an easy way to remember this? So I do it in terms of, if I go on to orange, I think about it in terms of if you can understand or if you know which one is, which direction is endothermic or exothermic, the exothermic direction is releasing energy. So it's giving off the energy as heat. So I don't remember these, I don't memorize it, I work them out. So if you know which side is giving off heat or where the heat is going to be produced, so in this case, it's the forwards reaction is exothermic. So the forwards reaction is giving off heat. So then if you increase the heat in the same way when you're doing concentration, if you increase the concentration of a product, it pushes the equilibrium away from that or in the other direction. So if we increase the heat, it's going to push the equilibrium away from that. So in this case, in the backwards direction. So I never memorize these. I always just work them out. But you can memorize them. Create yourself a nice table and memorize them. But I always work them out. Sorry, KK. I changed them because this said delta H is greater than 0. But I should be talking about the forwards reaction being exothermic. And if the forwards reaction is exothermic, then delta H, the change in enthalpy, should be negative. So it's not greater than 0. So that is wrong, is why I've changed it, because I hadn't recognized that we've got that incorrect there. It's the wrong way around. So delta H in this first, my blue box, should be less than 0. Delta H should be less than 0. i.e. it's negative, and in the right hand box delta H should be greater than 0. I've put 1 there and I mean 0. Sorry, maybe that's a typo, I think. Okay, because normally we talk about the forwards reaction. Whenever we talk about, if we've got a reversible reaction, we say it's an endothermic reaction, we're talking about the forwards reaction. is endothermic or exothermic. And that's why when you get a reaction, your little delta H is put on the right-hand side, because that's telling you the forwards reaction has that enthalpy change. So whatever the forwards reaction is, it gives you the enthalpy change for it. So we know that that's talking about the forwards reaction. So in this case, the forwards reaction is exothermic. So what happens when we increase the temperature, it tries to decrease the temperature again. And in doing that, it has to do more of the endothermic reaction. Yeah, exactly. Like Daniel says, it's always forwards unless otherwise specified. Lovely. Right, we're going to need to move on because I'm way behind. Let's do this last two things, and then I'm going to need to, we won't have time to do the exam questions, unfortunately, but never mind. So effect of pressure. For any gaseous reactants or products, the position of the equilibrium will be affected by changes in pressure. Notice that not all of these reactants are gaseous, only some of them are, so just bear that in mind. So if we increase the pressure, what's going to happen? Which direction is our equilibrium moving for an increase in pressure? Yes, these are reversible arrows. That's the one. Yeah, good spot. Good. We're going to the side with the fewer gas moles. Brilliant. We look for the side with the fewer gas moles. And in this case, it is the right-hand side. So if our right-hand side's got fewer gas moles, then if we increase the pressure, the system is going to move to produce more of the reactants where there are fewer gas moles. So this shifts the equilibrium to the right as there are fewer gas moles. That means it's going to decrease the pressure again. So we've increased the pressure, and in order to decrease the pressure, it's producing fewer gas moles, which decreases the pressure again. So we're going to get more products produced in this case. Good. And then on the other one, if we decrease the pressure, then it's basically the opposite. So I always find a way that you understand it. So in my case, it's increasing the pressure. I understand that one. So when I'm doing the opposite, I just have to think the opposite. So if I'm decreasing the pressure, instead of going for the fewer gas moles, I need to go for the more gas moles or most moles. So in that case, it would be shifts the equilibrium to the left, as this is the side with has more gas moles. So in this case, we're going to produce more reactants. If we increase the pressure with this system, whatever this system is, then we will get more products. If we decrease the pressure, we will get more reactants. Good. Okay. Final thing that I wanted to mention is catalysts. What effect do catalysts have on the position of equilibrium? Oh, great, Liz. I'm glad. That's great to hear. Thank you. Good. What about this effect of catalysts then, guys? Good. Well done to those of you that have spotted straight away they don't have an effect. And they like to chuck this into an exam question just to see if you're paying attention. So catalysts have no effect on the position of equilibrium. What do they affect though? Position, whoops. What do they affect? Because they do have an impact on something, but what do they affect? No. Whoops, go back. I meant to write no effect. What do they affect? Good, they just speed up the rate of reaction. They speed up the rate of both the forward and backwards reaction. And because of that, because they speed up the rate of the forward and backward reaction, then we would get to equilibrium faster if we were to start from scratch with a catalyst, if we were to chuck some reactants into a pot with a catalyst, they would reach equilibrium faster because both reactions would be, both rates of reaction would be happening quicker. So we'd get to equilibrium faster. However, the position of equilibrium would not change. Good. Lovely. And well done. Yes, they do. Catalysts do provide pathways for the reaction, alternative pathways with a lower activation energy. So that's very good. But the key point for this lesson anyway is that they have no effect on the position of equilibrium. They can't change where the equilibrium lies. Lovely. Is saying use up okay terminology in the exam? You don't actually need to talk about why the position of equilibrium shifts usually in an exam. So you don't have to include the bit about using up. Normally, all they want from you is a description of where the equilibrium has moved. So it's moved to the left, or it's moved to the endothermic reaction direction, or something like that. So you don't actually need to use them, use that terminology. I've just popped it in there in order to help with our understanding. But great question. Okay then, team. So how is everyone feeling about that? And then we are going to finish up. No, Jake, sorry. We do say at the beginning of the PowerPoint that we weren't looking at Casey in this session, just at the theory and Le Chatelier. Hope that's all right. So how's everybody feeling? One, smiley face, straightforward, we're all good. The effect of temperature on equilibrium is always confusing. It is. I suggest practice, and find a way of turning it into a visual thing, I think, is often very useful for students because it's such an abstract concept. I'd find a way to make it a physical thing, just to visualize it on the page. Okay, fantastic, guys. So unfortunately, we don't have time to do these exam questions, but we have gone through reversible reactions, Le Chatelier's principle, and the application of Le Chatelier's principle. But just want to let you guys know that we've got some upcoming web classes coming on. So if you're interested, please pop some reminders on YouTube to have a look at those. We also offer A-level chemistry tutoring, so we haven't had time to go through these questions now. However, we do offer things called drop-in classes on our YouTube, on our website, which are classes dedicated to just going through exam questions or going through whatever topic it is that you, as the tutees, want to go through. So we have web classes where we are doing live classes, where we go through, just as we've done here, the content and topics, and look at some questions together. And then we also have these things called drop-in sessions where we just go through things that students have requested. So a specific part of a topic that somebody wants to go through, or a specific exam question that somebody wants to go through. So these are all offered on our website. And so if you pop on there and you use the code tutor7, TUTOR7, then you can claim 1 week free trial. Come and see what it's like, see if it's the kind of thing you might fancy. The code is in the chat if you want, so please have a look on there and potentially use that to get a 1 week free trial. I'm also just going to show you on the website how to use that code or where to go, because it is, unless my laptop freezes, it might not want me to. Okay, so I will pop us on to here. Where's the SnapProvise web? There it is. Okay, so hopefully you guys can see the SnapProvise website now. So if you go, I'm currently already on the tutoring page, but if you click on the 3 dots, the hamburger sign on the top right, and then click on tutoring, it'll take you to the tutoring page. And if you scroll down on the tutoring page, find A-level chemistry, if that's what you're interested in, which obviously I am. If you go onto there, and then again, scroll down to the bottom, it shows you everything that we offer, including some more videos, so you can see some free sample classes. And right at the bottom, when we get there, is a schedule. So it shows you all the classes that we have coming up. So in May, for example. We've got some year 13 classes, some drop-in tutor sessions, so we've got year 12 alcohols, and we've got another drop-in tutor, etc. So you can use this to plan your time and work out what you can use, or what you want to come to, what you want to spend your time on, and you can submit your own questions and stuff for the drop-in sessions. So this is all on offer on the website. So please feel free to head along and have a look, download any of the free resources, have a look at the free sample classes, but also have a look on our YouTube. There are loads of loads of previous classes for you to have a go through on our YouTube channel. So please feel free to look at those and download the slides for those, etc. So if anybody has any other questions, I will hang around for another minute and just answer some questions, and then I'm going to need to disappear. So yeah, massive good luck to everybody who's got their assessments coming up. I wish you all the best of luck if I don't see you between now and then. So please, yeah, I hope that everything goes well for you. And yeah, I've got everything crossed for you. So please, yeah, so thank you so much for coming. It's been really great having you here. I'm so glad that this has been useful to some of you. So thank you very much. Maya, in answer to your question, we wouldn't mark personal work, but you could submit an exam question for a drop-in session, and then we would go through it together. So we wouldn't be marking personal work, but we could go through questions with you in a drop-in session if you were part of our service, but we wouldn't mark specific questions. So otherwise, thank you so much, guys. Yes, we do go live every Sunday, but it varies which topic we do, what's the word? Subject. So biology, chemistry, physics, maths. We rotate throughout them, but we do usually have a live session every Sunday. Just check on the YouTube channel for look at our upcoming classes to see what are scheduled. We're just scheduling May's and June's now, so hopefully they should be up on the website as soon as possible, up on the YouTube channel, sorry, as soon as possible, so you can use that to schedule classes. So have a lovely rest of the evening, guys. Drop-in sessions are for registered people only. The YouTube live schedule has just been popped in the chat, so please have a look at that if you're interested. Otherwise, any other questions, then you can email us at hello@snapprovides.co.uk, and they will try their best to answer all of your questions. So please feel free to drop them an email, but otherwise have a lovely evening, everybody. Go out and enjoy the rest of your holidays if you're still on Easter holidays. And yes, have a lovely, lovely time, guys. Thank you very much. Speak to you soon. Well done. Thank you very much, everybody.